90 18 terabyte hard drives, 1.6 petabytes of raw storage. You can just buy this? Yeah, serverpartdeals.com. We're gonna do a build. It's time to build a petabyte server. Don't worry, I'm going to walk you through it. You can do a petabyte of storage in just 4U. Yeah, you can actually do 2.5 petabyte. I mean, if you get super insane capacity drives, we're going to use 18 terabyte drives. This is a chassis from Supermicro. It's actually a disk shelf. It's not a server. And that's what I recommend when you're building something this insane. Come with me on a journey of exploration and learning, and you can see why I think this is the best way to approach having a petabyte of storage locally. We're going to do this because Backblaze lost some data in the cloud, and somebody I know wants to have a local copy. That's probably going to be another video in the future, but for now, let's walk through the learnings and recommendations and everything else if you're going to embark on a project like this. Why a disk shelf? I mean, what is it about a shelf of disks? It's like the name says, it's a shelf of disks. There's no computer in here. This is just the care and feeding of your actual hard drives. Why a disk shelf? Well, I've been building these things for a long time. I've helped a lot of other content creators with their storage. And for home lab and off-label use, older NetApp disk shelves were the way to go. Those are the 10-year solution, 7 to 10 years ago. NetApp, you say? The venerable old NetApp. Love these things. They're wonderful. I still have a few that I'm giving away to content creators and that sort of stuff. There's nothing wrong with this for a home lab or anything like that. It's 24 drives. It's just that, those power supplies have been on a long time. The interface is slower. SAS 6 at best. SAS 3 is more typical. They're not bad. It's just they're not a 10-year solution. And they're not something you would run a business off of in 2025. NetApp. It's good stuff. This is the modern 10-year solution in 2025. This kind of approach means that your storage lives here, but it's got connections to a server in the back, and so you can actually swap the server hardware independent of the storage. That makes error recovery a lot easier because the computer does something weird. This is modular. This is built to hold a lot of drives. This is way better than a chassis that is going to hold a lot of drives because it's a little bit separation of concerns. Recovery generally is a little easier, but this still has some really cool features like out-of-band management. You can plug it into the network and it'll tell you information about the chassis. It's also modular design, so the power supplies, the interface modules. This one is set up for SATA. You can set it up for SAS, serial attached SCSI, which we'll talk about, and SAS is a little bit more redundant in that you can have redundant paths to the drives and redundant connections to the drives and even more redundancy. But considering this is meant to be a mirror of information that is also mirrored off-site in a cloud service provider, you probably don't need that level of redundancy. If you were using this for nearline storage or you wanted it to be a system that was up all the time, then maybe serial attached SCSI would make sense. There's really not a lot of cost differential between SAS and SATA, but you do physically have more hardware in the disk shelf as well, so it does make the disk shelf a little more expensive. And let's talk for a second about SAS versus SATA. We've covered this a lot in the past. These are SAS drives, these are SATA drives. The big difference with SAS versus SATA is that SAS drives are built for enterprise reliability, and they have some different features. As a practical matter in 2025, in terms of longevity and feature set and all this sort of thing, enterprise-grade SATA drives, which is what these Western Digital drives are really not a lot different than their SAS counterparts. The big differences that remain are the interface type. So they can do up to 1.2 gigabytes per second on the interface speed, but don't worry, the physical drives themselves, they're not actually any faster, it's just the interface speed. The other thing is that each of these drives support a redundant connection. So with SATA, you only have the one connection on the drive, but with SAS, there's actually two connections. The controller on this drive can be connected to up to 2 different controllers. This opens up some really interesting possibilities in terms of being able to connect this one disk shelf to a bunch of controllers. If you've got advanced software, like TrueNAS offers commercial software, this is not the free TrueNAS, but this is a paid for one. They offer solutions where you have multiple compute nodes connected to one disk shelf, which gives you a higher level of availability. Synology, they have the SA3400D. It's 2 compute nodes connected to storage, and in those cases, they require SAS drives because those are the only drives that will let you physically have 2 connections to 2 different controllers for high availability and redundancy. So if you lose one controller, the other one takes over. You can do some magic with interposers and connectivity in order to have redundant paths to a SATA drive in an enclosure, and Supermicro has some of that magic, but the single controller or single I/O module disk shelves are really not designed for that level of redundancy. You can add the features to that. This one chassis will take those upgrades, and you can do that, but for SATA drives and for the stated use case of this is a mirror of another backup, or this is where the backups will be staged from to the cloud, we don't need that level of redundancy or dual pathing. So SATA is just fine. The other reason to use SAS over SATA is signal integrity. These things can push a signal a lot longer, but because we're using a disk shelf that has electronics, it has stuff in it to repeat them, and so this is a lot different than using a long cable. If you use a SAS controller in a desktop computer with a really long cable, it may be a little bit unreliable with a SATA drive, whereas with a SAS drive, it would be perfectly fine. This is owing to the different electrical characteristics between SAS and SATA. But that doesn't really matter for what we're doing here. If you get a disk shelf, you sort of sidestep all of those problems from having to worry about it versus trying to assemble it in a chassis and mixing SAS and SATA. And it's like, did you have good cable integrity and blah, blah, blah. So let's just get this thing put together and run some benchmarks. This chassis is from Server Part Deals, and it's Supermicro, and I've actually used this chassis before. Actually, Jake from LTT, he and I worked on it a while ago. He has some really good notes about the particular setups that we'll get into, and there's a how-to for that on the forum. But Server Part Deals for, we could basically be out the door for less than half, really less than a third of the price of the equivalent system from Dell, and Supermicro is good stuff, and so you're going to be able to get parts for this chassis from now until the end of time because it is so popular in the enterprise and the cloud and everything else. See, that's the thing with the NetApp. It's like the reason you use the NetApp is because you can get parts. Oh, the power supply exploded. Oh, I'll just get another one. It's just that now there's so old and so many people are still using them that they're starting to dry up a little bit. That'll be a problem for this thing in 10 years. I want to talk about the care and feeding of a system like this because it is kind of complex. And as we do the video, it's like, oh, I've got my heavy-duty work table here. We're going to set it up on the work table and move it into place. No, this is the wrong way to do that. These drives, the thing that kills hard drives, clacking them together, just the mechanical stress of that is too much. These are ancient drives. Don't worry about it. But also, you want to move the chassis into place and get it mounted in your rack. This is about 300 pounds. Can your rack actually handle this unloaded? And then you add a bunch of drives to it, and it basically becomes immobile. You don't take the top off of it, you hit the buttons, and the whole drawer slides out. With drives in it, it's going to be immobile. If you need to move it, you need to set it up on a desk and test it as we're doing here. Then you have to take it completely back apart again, put the drives in safe transport, and transport it that way. If you transport this with drives installed, it's metal on the inside, not drive on drive metal, but it is metal on the side of the case. Vibrations are the enemy of computer equipment. Vibrations is what will kill things, and it's the same sort of drive-on-drive clack. When you realize that vibrations are the #1 enemy of longevity and reliability in computer equipment, you start to think about things a little differently. Maybe you're going to move your stuff into place with something like this. You can do that, but it should be boxed up in its original packing foam so that the vibrations are absorbed. Maybe you have a crash cart? My, how the turntables. This is actually the party cart, but if you have a crash cart like this in the data center, even putting the server naked on this, it's still going to endure a lot of vibrations and it's not good. Doubly so if the hard drives are installed. Do not transport or move one of these with the hard drives installed. The longevity of all of the drives will thank you, and or your CTO will thank you for doing it that way. Always pull the drives from the chassis, put them in their proper packing boxes, and transport them that way, and then transport the chassis, and then reassemble in the rack. It's got a fancy drawer. Use the fancy drawer. It's amazing. Just roll with it. It's good. Even if you got a good crash card, it's not good enough. Party! Let's take for a second to appreciate just how anachronistic mechanical hard drives are. This is a precision mechanical instrument. It has a motor in it. Well, two motors. Well, a motor as you think of a motor, and a voice coil, and it can access with precision 250 trillion bits on those spinning platters. It's the Rube Goldberg machine of storage devices. I can't even believe it. How insane is it that it's like a pocket watch. It's like, oh, here's your grandfather's precision yes, this 250 trillion bits stored with helium. Like, what kind of mad, crazy science is this? That this is it's steampunk. It's basically living steampunk. So this is one of the things to be aware of in your chassis. This can die. This is a port multiplier. See, we've only got 24 SAS channels at the back, but there's 90 drives here. How does that work? Well, that's what these are for. These take those serial attached SCSI channels and break them out into 3 zones. There's a zone here, a zone here, and a zone here. And if you were going to run SAS, you would need, to fully populate it. But each one of these drives is not really a dedicated path all the way back to the system. And so if you do the math really quick, we have 28.8 gigabytes per second with our 24 SAS 1.2 channels, which means that each drive individually can manage about 300 megabytes per second before it bottlenecks. And so if you're going to fully populate this, it really only makes sense to populate it with normal drives. Dual actuator drives can move at 500 megabytes per second plus. SATA SSDs can move at 550 megabytes per second plus, and serial attached SCSI SAS SSDs can move at least 600 megabytes per second, some of them upwards of 1.2 gigabytes per second. And so all of those things in this kind of a chassis would bottleneck. This is really just a bunch of disks. It's in the name. Disks, not SATA, not solid state, but spinning rust. And so on the forum, we talk about configuring this thing. Now, it's got an Ethernet port on the back, and you plug that in, and you'll want to update the firmware, and you'll want to update the out-of-band management. Those are 2 different firmware images. This, because it has 3 different zones in it, you don't have to use all 3 zones. If you just have one 16-channel external controller, you can make all the drives available. But the front zone will have double the bandwidth as the 2 rear zones when you do that. Otherwise, you need 2, 4, 6 groups of 4 serial attached SCSI channels to 2 16-channel controllers, and you end up using 12 channels on each controller, which is fine. That gives you a little bit of redundancy. But how you cable that is important, and there's a diagram for that on the forum. So you want to look at that and use that in order to get the maximum best possible performance. If the maximum best possible performance is not important to you, then it is possible to configure other zone configurations and just make all of the drives available even on a single group of SAS channels. Like, that's fine. But for the benchmarks and everything else we did the optimal bandwidth configuration so that there was no bottleneck as much as we possibly could in this chassis, and we used all 24 SAS lanes. So there's your out-of-band management port that you can load your firmware update to, and then you've also got your 3 groups of 2 for your serial attached SCSI channels, your A, B, and C. And depending on how you want to cable it and what you're using for your controller, like I say, you can use an 8 or a 16 channel controller up to 24 for optimal bandwidth. If you're not going to fully load this with drives, then you can get away with 16 drives and full bandwidth. Just know that 3rd zone is not necessarily going to be there or work for you. And then for fans, these are pretty standard fan modules. There's 6 of them. There's actually 2 fans in here, so this works really well for cooling. Dual 2,000 watt power supplies, also from Supermicro. These are infinitely standard and will be available from now until the end of time. These are 80 plus titanium, so very, very good power supplies. 2,000 watts, 120 or 240 volts. These chassis from Server Part Deals, they're the real deal. And if one chassis isn't enough for you, 2 petabytes, 1.5 petabytes in 4U, you can actually connect up to 3 of these, as you can see in the diagrams, also in the how-to on the forum at level 1. So, 7.5 petabytes in 3 times 4U plus the controller node. Yeah, that's pretty nuts. Now, for the controller node on this, you can go traditional EPYC, AMD EPYC, especially the F-series CPUs. Those are a good choice. Just to see how much we can get out of it, I'm going to start by using a 16-core AMD EPYC in the AM5 socket. Yeah, the new AM5 EPYC CPUs. If you're just using this as a backup server, The 16 core will get it done. 64 gigs of memory, well, 96 gigs of memory. You can get a lot done with that. And so that we're going to roll with that for our initial setup and our benchmarks. Pretty much the only option that I'd recommend for the controller is the LSI 9516i, 9500 series. These are SAS 12, 16 channels. Ideally, you have 2 of them so that you have, you know, a total of 32 channels. You're only going to use 24 of them. But hey, a little redundancy, a little controller failure, it never hurt anybody. These controllers do expect server levels of airflow. So if you're DIYing some sort of a control node for this, just understand you're going to have to point a fan at these cards because they do get warm. They don't have their own cooling. If they were using a desktop computer, they absolutely would need their own cooling solution because they do get really warm and toasty. Now, for this kind of a layout, again, generally I'm recommending that you only use 88 of the 90 slots and you reserve the other 2 slots either for hot spares, which means that you add drives and the system doesn't use them until something goes wrong with the other drives. When this baby hits 88 drives, you're going to see some serious or you keep them empty so that when you do have a drive problem, you can put a drive in the empty slot and let it image. One of the things with ZFS, which is what I recommend for this project, for your file system, for this kind of geometry, it sort of goes without saying, you should check out our other ZFS content, is that when you have a drive anomaly, generally it's better than pulling the drive that had the anomaly. You just add a drive and let ZFS move the stuff from the drive that had an anomaly or the drive that disappeared. It'll recreate it somewhere else. You've got the option also of running different RAID Z configurations. You could, well, I mean, with this many drives, you could do a striped mirror configuration, which will be absurdly fast. But again, probably not like this kind of a chassis for a striped mirror configuration probably doesn't make sense because of the SAS expanders. You buy this kind of a chassis for capacity. You're not really worried about off-the-line performance. And so I wouldn't recommend a striped mirror configuration unless you really know what you're doing. So RAID Z, RAID Z2, RAID Z3, and multiple VDEVs. You can set it up just like it's got zones. You can stripe your drives across zones and get a lot of performance out of it. That's what we've done with the benchmark breakdown, which I'll get to in a second. You can check out the forum for more details. You can also do DRAID. Generally, you don't really use DRAID unless you've got a very large number of disks, but this is a very large number of disks. And if you want to maximize your space, you could do, you know, a 3 drive, like DRAID 3, and then keep 2 drives as spare. And so you end up getting something like 85 of your drives worth of capacity, and any 3 drives across the whole pool can fail. That's perfectly fine and reasonable. But to get into these specifics with the VDEV configuration and everything like that, I'm going to have to get to a terminal so that we can talk a little bit more about specifics and what we saw with FIO. We're using this little thing. It's AM5. Epic is a thing for AM5. This has got 2 of our 8-channel LSI SAS controllers. I just have to unpack a lot of cables. And then we got to follow the helpful wiring diagram. There's a Serenity reference. 2x2 connectors of blue. So all these discs are very fast, and each pair gives us a faster connection back to all of the discs. Yeah, we just want to make sure it works.
It's burning.
It's burning. So once you get your drive set up, you run tests. That's what you do, right? We got all kinds of tests. Even before we set up ZFS pools and everything else, you just run a lot of tests. Basic stuff. Smart CTL, Smart Mon Tools is useful for checking the drive. How many power on hours does it have? Power on hours, 27,687. Not a big deal for drives like this, 18 terabytes of storage. I mean, it's fine. You get a warranty from server part deals. The helium level looks good. I also like to do a test. So with the way we've got it cabled, there should be no bottlenecks. So I've selected 24 drives, basically along the center column, and we're going to run a read test on all 24 of them simultaneously. And basically you're looking for about 200, 250 megabytes per second from every drive. And we can see, boom, all 24 of the drives that I randomly selected in our chassis are running at full speed. And so this tells me that every channel that's connected across both controllers is working correctly. I'll do some more tests like this with some more randomly selected drives just to make sure there's nothing really strange going on, but generally this should work like this. Now sometimes you run this test and you'll get an absurdly low result. The drive may have been doing something in the background, or the connections may be asleep. If you only test one drive at a time, it might be oddly slow, and that's because the link's powered down to save power. And so it's using so little bandwidth with just one drive active, you may have to run it a couple of times for the chassis to wake up. But this looks pretty good. Let's get somewhere a little quieter and back to the terminal. Actually, this is astonishingly quiet considering it's a petabyte. Like, somebody almost wouldn't complain about this if it was on their desk. Almost. $90 drives? It shows us 180. Well, it depends on where you check. If you look in disk by ID, you'll only see 90. But if you look in disks by connection, you'll see 180. And that's because there's a redundant path provided by the chassis. Even though we don't have a fully redundant path with the 6 connections to the 2 controllers, we kind of do have a redundant path. Even though this chassis is not configured with the extra redundant path interface. Like, we should have that. It would be nice to have that. But if we really wanted true full redundancy along with the interface cards, but even in this configuration you do have a redundant path to each drive, at least part of the way. Okay, so we did our smoke test and we did our burn-in test. Can I get 250 megabytes per second from basically all 90 disks at the same time? Basically, yeah. It performs really well. I've got a Z-pool created. I've got 9 VDEVs of 10 devices each, RAID Z2. And so this is one of the best performing, best balanced pools that you have, but I've already violated my own rule. I'm using all 90 disks. I didn't leave any spares. But the nice thing with this is that any 2 disks could fail, guaranteed. If you have a third disk that fails, odds are it still won't fail. You can lose any 2 disks in any RAID Z VDEV. So if you lost 3 in one VDEV, you're going to lose the whole pool. But if I lost 2 in this VDEV and 1 in this one, the pool is still going to keep running. So that's nice. The bad thing with this is that I'm going to have to pull a drive that's malfunctioning or dead in order to replace it. Fortunately, the front of the drives are all etched with the serial number, so you can, like, it's pretty easy to shut the pool down and it's like, look, and it's like, ah, yes, I've confirmed that this one is the one that has disappeared. All right. That's the drive serial number that I'm looking for. So for an offline backup type solution, this is great. I know that some enterprise configurations, you really want to hot swap the drive. It's like, oh, that's really cool, but it's a lot safer to shut everything down and then just go disk by disk and just double, triple, quadruple confirm. But you can't see the front of the disk. And I mean, you could do it hot if you want to live dangerously. But if you want to play it safe, you can shut everything down and do it that way. Even just doing a couple quick FIO tests without a lot of complexity, things are looking pretty good, but I'm actually going to have to run something a little bit more complicated to test our IOPS and latency and everything else, and that's bench FIO. And that's something I want to get into in another video, but I'm also curious about what disk configurations you want to see. I want to test this RAID Z2, this 9 VDEV wide RAID Z2 configuration, but I'm also thinking about a couple of specific DRAID configurations. And I mean, you know, maybe we could throw in a striped mirror just for fun. It's only 45 drives of capacity, but we would actually be using, you know, that's sort of the maximum speed. And then any one disk can fail. And chances are, if a second disk failed, it wouldn't be fatal. But there's a small chance that, you know, just a few percentage points that it would be fatal if a second disk died. And then maybe some RAID Z3 configurations just to see how that works. So it's going to take a little while to run these, as it turns out, because with disks this large, it's like, oh, I'll just do a 100 gigabyte test. And it's like, that's a little misleading. You really need to test like a terabyte or 2 or 3 at a time when you have 90 disks that are 18 terabytes each. Even just testing here, it's like we've used 8.24 terabytes, but I've still got 1.09 petabytes of availability. I mean, without really even doing much, 5,000 megabytes per second on a ZFS file system? Do you know how absurd that is from a mechanical file system? That is just completely insane. And remember, this is an AM5 system that doesn't have a lot of RAM. It would be even faster with a true EPYC CPU and lots of RAM. Even just doing some quick testing here, I mean, I've already used 8.24 terabytes, and there's, you know, just over a petabyte still available. And to get really good testing, you really need to put a lot of information in the pool. So that's going to take a little bit when you've got an array this large, because, you know, it's fun. So stay tuned for part 2. Get subscribed, check that out. Maybe go check out some stuff on Server Part Deals. You don't have to buy a petabyte at a time, but I haven't had a disk die yet, and I've been doing bad things to them for several weeks now. So we'll see. All right, signing out. You can find me in the Level 1 forums.